Inside every modern laptop, smartphone, desktop computer, advanced AI server, or practically any other high-tech device are cutting-edge microchips such as the CPU, GPU, SOC, DRAM, and SSD chips, each with tens of billions of transistors inside of them. The transistors inside these microchips are incredibly small, with the tiniest features measuring around 10 nanometers or 45 silicon atoms. This feat of science and engineering may seem impossible because, on one hand, each of these microchips is made from connecting billions upon billions of transistors together, and then, on the other hand, each individual transistor is only nanometers in size. Additionally, these microchips are everywhere and in everything, and therefore they must be reliably mass-produced. So how is manufacturing such a microchip even possible? These are photolithography tools, and they're the key to manufacturing microchips. However, it's important to note that there are dozens of different types of tools used in the various steps for making microchips, and each one plays a critical role in the manufacturing process. So, to be accurate, photolithography tools are the ones that are used to copy and imprint the nanoscopic patterns of transistors and layers of wires onto a microchip. And therefore, a useful analogy is to think of these photolithography tools as nanoscale microchip photocopiers. Photolithography tools have been continuously evolving to copy and imprint smaller and smaller transistors and circuitry. And in this video, we're going to dive into this state-of-the-art EUV photolithography system and explore the science and engineering inside of it. So let's begin with a quick overview. To start, the EUV lithography machine takes the design of a single layer of a microchip on what's called a photomask and loads it into the machine. Next, a 300mm silicon wafer with a set of prior processes applied to it is placed onto a wafer carrier inside the machine. With both in place, the machine uses extreme ultraviolet light, or EUV, and a set of mirrors to copy the design from the photomask onto a silicon wafer. The wafer moves to the next position, and the microchip design is copied yet again. This copying happens over and over until the wafer is filled with 100 or more microchips, and then a new wafer comes in and the copying starts over. This is the real-time speed of the lithography machine, taking about 18 seconds to duplicate the same microchip design around 100 times across the entire area of a 300mm wafer. Let's take a look at one of these microchips and see what exactly we're copying. Inside this microchip are approximately 30 billion transistors, and if you were wondering, it's the design of a GPU or graphics processing unit found in the center of a graphics card. When we zoom into a nanoscopic view of this microchip, we find a 3D maze of transistors and layers upon layers of wires with the smallest dimensions of the bottommost layers measuring around 10 nanometers or around 45 silicon atoms. Specifically, the EUV photolithography system typically patterns the lower layers with the smallest features, whereas other photolithography tools are used to pattern the higher layers. It might be difficult to fully grasp the level of detail and complexity inside a single layer of billions of nanoscopic transistors. So let's use a thought experiment and pretend that instead of copying transistors and wires, this EUV photolithography system is used to copy the text from a book. If the width of each line of a letter is 13 nanometers, then the word cat would take up around 155 by 240 nanometers. A page of text would be about the size of a red blood cell, and a chapter of a book would be a grain of pollen. When we zoom out to see the equivalent area of a GPU chip, how many pages of text do you think we could fit using these nanoscopic letters? Well, we could print all 7 Harry Potter books, plus every book written by Stephen King, the entirety of the text from the English Wikipedia, and still have enough space to fit every single book from your local public library. There's an unbelievable quantity of nanoscopic lines and details that can fit into the area of a microchip. And it's all photocopied by this EUV lithography system in less than a second. It's no exaggeration to say that every piece of modern technology that you use is made possible by this machine, and in this video, we're going to explore the key modules inside it and see how they work. So let's jump right in. This video is sponsored by ASML, the company that designs and manufactures EUV lithography systems. Throughout the video, all the details and facts were independently researched, written, and animated. Additionally, some aspects are simplified, and due to the proprietary knowledge and confidentiality around EUV lithography, some of the details we present are approximated or modified. Before we open up and explore this EUV system, let's first spend a few minutes discussing microchip manufacturing in semiconductor fabrication plants, or fabs for short, and the exact role of this machine. Inside our example fab are hundreds of machines, of which a couple dozen or so are the EUV lithography machines we've been discussing. To make a microchip, 300mm silicon wafers are stacked inside a front-opening universal pod, or FOUP, and carried from machine to machine using an overhead transport system. The FOUP is lowered onto a machine where each wafer is processed in one way or another, and once the machine completes its work, the wafers are returned to the FOUP. The pod is picked up, carried to the next machine, and dropped off for the next step in the process. Microchip manufacturing is incredibly complicated, but a simple way to think about it is that it's kind of like spray painting a design through a stencil, but instead of art, this stencil contains the nanoscopic patterns used to build the transistors and wires. Inside the microchip factory, some tools are used to build a stencil such as the EUV lithography system, and many of the other machines, such as the deposition tools or ion implanters, are the spray paint. So let's take a look at how we build a stencil on the wafer, which is technically called a photoresist layer. To begin, the wafer travels to a machine called a track tool, where a light-sensitive material called photoresist, or just resist, is poured on and evenly spread across a spinning wafer. Next, the wafer is heated in order to dry and solidify the resist, thus forming a flat blank stencil. The wafer then moves to the photolithography tool, where EUV, or extreme ultraviolet light, is projected onto the photomask, which is also called a reticle, but typically just a mask for short. When EUV light hits the mask, the patterned information is imprinted in the light, and this imprinted light then bounces off a set of mirrored lenses in order to project a focused and scaled-down image of the mask onto the wafer. Wherever the EUV light touches, the resist is modified, and thus the design is copied from the mask onto the wafer. The wafer moves to the next position, and the EUV patterning process repeats again until the entire wafer is filled with copies of the design from the mask. Next, the wafer travels back to the track tool, where the modified resist is washed away using a developing solvent, and the water is heated to form a hardened stencil or completed photoresist mask layer on the top of the wafer. Now that the wafer is patterned, the wafer travels to the other spray paint-like tools in the fab, which are used to etch away the uncovered areas, implant dopants such as boron or phosphor, or deposit a layer of copper, tungsten, or other metals, thereby building a single layer of nanoscopic structures. Note that there are additional process steps that we're not going to get into. Now that we have a basic understanding of how the stencil and spray paint-like processes form a single layer, let's zoom into a nanoscopic view inside a microchip, where we can see how the transistors and wires are incredibly complicated three-dimensional structures. Each of these layers are built one after the other, starting with the transistors at the bottom, moving up to the small wires, and then wider and wider metal layers further up. In essence, to build a complete microchip, the stencil and spray paint process is repeated over and over each time, building only a single layer, and therefore it's more effective to visualize these processes as a loop, where a single pass of the loop forms one layer using a single mask design in the lithography tool, and then another layer is built using an entirely different mask loaded in the machine. To complete a GPU chip like this one, the series of process steps, or loops, is repeated around 80 times, resulting in around 1,000 individual process steps and taking 4 or so months to complete. Let's go back to the nanoscopic view of the microchip. Here we can see that the lower layers are incredibly tiny, and 13 nanometer EUV light is used to build the pattern for these layers. However, the upper wires are substantially larger and are patterned using an entirely different machine called a DUV, or Deep Ultraviolet Photolithography System, which is also built by ASML and uses a deep ultraviolet wavelength of light. DUV lithography tools were introduced in the 2000s and are still incredibly advanced machines. Because DUV tools typically cost less than EUV machines, it's more cost-effective to use EUV tools to pattern the transistors and so-called critical layers, and then use DUV tools to pattern the upper, wider, less critical layers. Additionally, less advanced chips that don't require the smallest transistors and wires may forego using EUV lithography altogether and only use DUV wavelengths such as 193, 248, or 365 nanometers. As a result, cutting-edge fabs typically utilize different types of lithography tools, and all these machines work as an intricate ecosystem to make a microchip. With the basics of microchip manufacturing covered, let's open an EUV lithography system, explore the incredible science and engineering inside, and divide the system into its 5 key parts: the light source, the illuminator, the reticle handler and reticle stage, the projection optics, and finally, the wafer handler and wafer stages. We'll begin with the light source, which produces the EUV light. But let's first answer the question of why we even need to use extreme ultraviolet light. Well, a simple analogy is to think of the light used to project and copy the pattern from the photomask as the tip of a marker. And, as you're probably familiar with markers, if you want to draw thin lines, then you need a marker that also has a thin tip. You can do tricks like angling the marker, but if you want to draw lines that are 100 times thinner, well then you need to switch pens and use a much smaller, fine-tipped pen. Likewise, to copy designs with dimensions only around 10 nanometers wide, we use 13 nanometer light, which is in the extreme ultraviolet light range of the electromagnetic spectrum. The more technical answer deals with the wave-like nature of light and what happens when light hits these nanoscopic patterns inside the photomask. These patterns are made from nanoscopic EUV-absorbing blockers on top of a surface that reflects EUV light. We'll explore the photomask and how the system uses reflective lenses a little later in this video. But for now, instead of using reflective optics, it's easier to visualize the photomask as through beam optics in a setup similar to the well-known double slit experiment. However, instead of the double slit, we're showing light passing through a complicated pattern of nanoscopic slits that represents a small portion of the overall photomask. So what happens when we use a wavelength of light that's substantially larger than the 13 nanometer EUV light, such as this 450 nanometer blue light? Well, when this large wavelength light hits the pattern is almost entirely lost. This is due to the width of the holes in the pattern being substantially smaller than the wavelength of light hitting it. This limit to the resolving power of the lithography machine is described in Rayleigh's Criterion equation, which we will explain later. So let's switch to 13 nanometer EUV light. As the EUV light hits the pattern, the light passes through and the pattern of the photomask is imprinted into the light, and the light diffracts similar to the double slit experiment. This imprinted light then passes into the projection optics mirrored lenses, which are used to focus and scale down the pattern and project it onto the wafer. So now that we understand the need for EUV light, the next question is, how do we produce it? To start, two high-powered laser pulses run through multiple amplifiers below the cleanroom floor. These laser pulses grow in power and then travel from the subfab using a pathway of mirrors and up through the bottom of the tool and into a chamber called a source vessel. The first laser, called a pre-pulse, is around 5 kilowatts in power and is targeted at a droplet of tin using a set of actuated mirrors. This pre-pulse laser turns the tin droplets into a pancake-like shape. The second, approximately 25 kilowatt main laser pulse, which is more than 10 times stronger than the lasers used to cut steel, hits the tin pancake, instantly vaporizing it and turning it into glowing plasma. Within each of the tin atoms, some electrons are ejected and others are kicked up to higher energy states. When electrons drop back down from the 4F to 4D orbitals, 13 nanometer EUV light is produced. Shooting two laser pulses at a droplet of tin might seem like a rather obscure process. However, EUV light doesn't naturally occur on Earth, and it's one of the few ways to efficiently produce over 500 watts of EUV light. Additionally, the reason for using tin is that its plasma produces a wide range of wavelengths with a clear peak at 13 nanometers. So, where does the tin droplet come from? Well, over here, a solid ingot of ultra-pure tin is melted and fed into a storage tank and then piped towards a microscopic nozzle. A piezoelectric transducer squeezes the tip of the nozzle, and, due to high-pressure nitrogen inside the storage tank, a droplet of tin is forced out at a speed of 100 meters a second. Next, high-speed cameras measure and calculate the trajectory of the droplet and feed the data to a set of actuated mirrors in order to angle the laser pulses to precisely hit the tin. To control the amount of EUV light, sometimes droplets are skipped by the lasers, and these droplets are captured over here. This process of producing high-speed tin droplets and then shooting them with two laser pulses to generate EUV light happens at a rate of 50,000 times a second. Now that we have EUV light, the first mirror, called the collector, focuses all the EUV light to a small hole called the intermediate focus, which only EUV light can pass through. The light next enters into the illuminator, which is composed of the field facet mirror, the pupil facet mirror, and another set of mirrors. These mirrors are so perfectly shaped that there's less than an atom's deviation from the surface. The illuminator takes this EUV light and shapes it into a thin ribbon that has equal uniformity across a well-defined range of angles before it hits the photomask. Using an equal uniformity of light at all angles is critical to imprinting a perfect nanoscopic pattern from the mask via the light and onto the wafer. We want to take a short detour and mention that this has been a rather challenging video to make, simply because there's a mountain of science and engineering inside these machines built by ASML, and this video only explores the tip of the iceberg. Essentially, a lot of the details had to be cut in order to keep this video a manageable length. For example, EUV light is incredibly difficult to work with because it's absorbed by atmospheric molecules, and therefore the entire light path and wafer carrier stage is connected to vacuum pumps which remove all the air. Additionally, EUV light is absorbed by glass and practically all other materials, and therefore to focus and transport the light, this system uses mirrors rather than transmissive lenses. However, these mirrors, called Bragg reflectors, are nothing like the mirrors in your bathroom, but rather they're composed of dozens of alternating layers of silicon and molybdenum, each only a few nanometers thick. When EUV light hits the surface of this Bragg reflector, only 3% is reflected at each boundary layer, while the rest passes through. But with so many layers, the cumulative 3% reflections add together using constructive interference, resulting in a total of 70% being reflected for a single mirror, while 30% of the light is lost and absorbed. However, with more than 10 mirrors in the optical system and only 70% reflection at each one, the final light hitting the wafer is less than 10% the brightness of the light emitted by the tin plasma, which is why the initial light from the source vessel needs to be as bright as possible. Another example of the incredible engineering inside this machine is that this field facet mirror is assembled from hundreds of independently controlled mirrors that can be angled to direct the light onto specific regions of the segmented pupil facet mirror. Together, these two mirrors take the cone of EUV light from the intermediate focus and turn it into a complex pattern of illumination. For example, this is called annular illumination. Here's dipole illumination, and then here's quasar illumination. You're probably wondering why we require such complicated patterns of illumination. Well, when we look back at the microchip, one layer of wires is running mostly horizontally. The next layer is a set of cylinders called vias. And then the following layers have wires that run vertically, and each layer uses a different mask. Earlier we said that the EUV light is kind of like the tip of a fine-tipped pen. Having different patterns of illumination is like holding the marker at different angles, with respect to the lines or circles that are being patterned. Specifically, annular illumination is best used to pattern the layers containing vias, and is like holding the marker straight up and down, whereas dipole illumination, like this, is best used to pattern lines running horizontally, and then we rotate the dipole illumination for patterning the vertically oriented wires. Imagine being at the forefront of this groundbreaking science and engineering. Then picture ASML, whose work powers the innovations that solve some of humanity's toughest challenges in energy, mobility, and healthcare. ASML is a leader in photolithography systems, serving as the backbone for the world's leading chip makers and enabling the technology that drives our future. With over 44,000 talented individuals and growing, ASML is headquartered in the Netherlands, with major R&D and manufacturing sites in the US and Asia. Their sprawling campus is not just a workplace, it's an exceptional environment where cutting-edge technology comes to life. To keep pushing the boundaries of what's possible, ASML seeks exceptional talent. They are looking for scientists and engineers ready to design the next-gen lithography systems, technicians and logistics experts eager to build, ship, and support these groundbreaking systems, and software developers passionate about working in a world of nanometers. ASML is the next step for those ready to make an impact in an inspiring setting. Together with their suppliers, partners, and customers around the world, they are committed to powering technology forward. Visit their website using the link in the description to learn more and start a journey with ASML today. Let's move on to the next part of this EUV lithography tool and explore the Photomask or mask, which is also called a reticle, and contains the entire design of a single layer of a microchip. The mask starts in a doubly sealed pod and is loaded onto the machine using an overhead transport system. The outer protective carrier is opened, and a robotic arm picks up the inner pod and carries it to a vacuum load lock. The chamber is sealed and pumped down to a vacuum, and the inner door opens. Next, the inner pod opens up and a separate robotic arm carries the mask and base to an inspection station. Each mask has a half a dozen different marks, including a barcode, as well as fiducials, which are designs used to align the mask with sub-nanometer level accuracy. The mask is carried over to and loaded onto the reticle stage, which moves back and forth across the EUV beam with incredible accuracy, and at high speeds with more than 7 Gs of acceleration. This mask's surface is built from the same Bragg reflector surface mentioned earlier, but with a pattern of absorbers on top that locally blocks the light in order to create the detailed microchip layer pattern. This 6 by 6 inch mask has a pattern area of 104 by 132 millimeters and an absorber pixel resolution of below 10 by 10 nanometers. In the beginning of this video, we showed a variety of different chips with different sizes, and shortly after, we showed a GPU being patterned across the wafer. The pattern on the mask is 4 times larger than the microchip, and this GPU chip is close to the maximum size chip that can fit on the mask, and therefore only 1 copy fits, resulting in 90 GPU chips fitting onto a 300 millimeter wafer. However, CPU chips are typically smaller, and therefore, in the following example, we can fit 2 copies on the mask and a total of 185 chips on the wafer. When we look at even smaller DRAM chips, 12 copies can fit on the mask, yielding 978 chips on the wafer. Technically, the exposure field is 1 scan of the mask onto the wafer, and an exposure field can have anywhere from 1 to a dozen or more die patterns on it, yielding around 100 to 1,000 or more chips on a single wafer. This mask contains an incredible amount of information, and as mentioned in the intro, it has the equivalent amount of detail as all the text of Wikipedia plus all the books in an average public library. This mask, which can cost around $300,000, must be so perfect that, using our analogy, there can't be a single grammatical error, spelling mistake, or even an extra curve on a letter across 21 million pages of text. Otherwise, it would damage every chip on the wafer. Also, if you're curious, here are the calculations we used for the transistors to text and book conversions. Pause the video to work it out. The next topics we'll explore are the projection optics and how the wafer is moved around the machine. But first, we'd like to mention that this video topic is incredibly complicated and took hundreds of hours to research, write, model, animate, and edit, totaling over 1,100 hours. So if you could take a few seconds to like this video, subscribe, comment with a quick message below, and most importantly, share it on social media and with a friend, family, or work colleague. It would help far more than you think. Additionally, we have a Patreon page with AMAs and behind-the-scenes footage, and if you find what we do useful, we would appreciate any support. Thank you. So let's move on to the projection optics. These optics are composed of a series of mirrors that are used to project and focus the patterned EUV light onto the wafer with extremely high accuracy, while minimizing wavefront aberrations and shrinking the image by a factor of 4. These mirrors are designed and manufactured by Zeiss, who is a long-standing partner of ASML and has been a vital collaborator in the development of the optic systems inside photolithography tools. To understand the projection optics, we have to discuss what determines exactly how small these wires can be, and for this, Rayleigh's Criterion equation is used. This equation states that the smallest dimension, or critical dimension, is equal to K1 times the wavelength of light, or lambda, divided by the numerical aperture, or NA. The wavelength of EUV light is 13 nanometers. K1 is the process factor, which relates to the various illumination settings created by the field and pupil facet mirrors that we discussed earlier, along with the photoresist and other factors, and is close to 0.3 for this machine. Finally, numerical aperture, or NA, is a measure of the angle and amount of light the mirrors in the projection optics can capture and focus onto the wafer. Numerical aperture isn't just about increasing the brightness of the EUV light, but rather it's more of a measure of the angles and amount of constructive interference wave paths that hit the mask and then are projected onto the wafer. In short, with a larger numerical aperture, or NA, which corresponds to a larger angle between the projection mirrors and focal point, we can achieve a smaller resolution. This tool has a numerical aperture of 0.33. However, the next generation of EUV lithography systems, called High NA, increases this to 0.55, resulting in an 8 nanometer critical dimension. Increasing the numerical aperture to 0.55 requires significantly larger mirrors, which results in a redesign of the entire optics system and other parts of the machine, thus considerably increasing the size and cost of the system. We could spend an entire video discussing the next generation High NA tool, but instead, let's move on to discuss the Wafer Transport System and wafer stage, and see how a wafer makes its way to the EUV exposure station. Let's start with a wafer that's carried in a FOUP on the overhead transport system. This FOUP lands on the lithography cluster, which is a combination of a wafer track tool and a lithography tool. The wafer first enters the track tool, where a layer of photoresist, or resist for short, is evenly spread across the wafer. The wafer moves to another area inside the track tool, where it's heated in order to dry and solidify the resist. Next, using robotic arms, the wafer is carried from the track tool into a vacuum load lock inside the EUV tool. The pneumatically actuated doors close, and the chamber is pumped down to a vacuum. Next, the back doors of the load lock open up, and a different robotic arm carries the wafer to one of the wafer stages. This system is called a twin scan because there are two complete wafer stages that concurrently move two wafers around. The key idea is that while one wafer is actively being patterned, a second wafer is being loaded onto the wafer stage and measured under an alignment sensor. Nanometer level accuracy is crucial with these machines, and one key philosophy of ASML is meten is weten, which is Dutch for to measure something is to know something. The reason for acquiring this level of perfection is that when we look at the nanoscopic layers of the microchip, which has wires and holes that are only 10 to 20 nanometers wide, if one layer is more than a couple nanometers off the previous layer, then the electrical connections won't conduct electricity correctly. And if an entire layer is off, then every single chip will be catastrophically destroyed. To make sure that the layer being patterned is perfectly aligned with the previous layer, the entire wafer is thoroughly measured by the alignment sensor. On the wafer are hundreds of alignment marks, which are reference patterns that assist in determining the exact position of the earlier layers of patterns. The alignment sensor meticulously measures the X and Y positions of every alignment mark on the wafer and builds a highly accurate 2D map from the results. This map shows some regions of the wafer being biased in one direction by a few to dozens of nanometers, and another region being biased in a different direction. Additionally, the leveling sensor uses grazing incident light to measure the exact height of the wafer, and builds a topological map of the wafer, which is critical for later bringing the wafer stage to the position such that the EUV light is perfectly focused onto the wafer. Now that we've measured and built the exact alignment and height map for the wafer stage next moves to the EUV exposure station. As the wafer is being patterned, the wafer stage moves in perfect synchrony with the reticle stage, but only a quarter of the distance due to the 4:1 reduction. At the same time, the stage makes nanoscale adjustments using the alignment map so that the new layer perfectly aligns with the previous layer. When the wafer stage moves from one exposure field to the next, it's important that no EUV light hits the wafer, and thus a shutter positioned up here near the reticle stage closes. Once the wafer stage is positioned to pattern the next microchip, the shutter opens and the wafer stage and reticle stage move in perfect synchrony again. This process repeats until the entire wafer is patterned, taking around 18 seconds in total. So then, what actually happens as EUV light hits the photoresist? Well, resist is a polymer mixed with a photoacid generator. When high-energy EUV photons hit the resist, the light ionizes it, releasing high-energy electrons. These electrons then hit the photoacid generator, producing an acid that breaks apart the polymer, making it weaker. As a result, the areas hit by the EUV light become soluble and are washed away by a developing liquid in the subsequent process step. One detail is that the resist has an extremely high contrast, meaning that at a certain level of EUV light, the entirety of the resist hit by that light is broken down. This is critical in producing sharp patterns and walls on the resist. Let's next explore how the wafer and wafer stage move around. Specifically, the wafer stages levitate on a large magnetic table composed of more than 1,000 magnets. Electromagnets on the underside of the wafer stage move it along this magnetic table both quickly and with micrometer-level accuracy, while interferometers on the top of the stage measure its exact position, and this setup is called the long stroke stage. In order to secure the wafer, it's placed on a plate, which is technically called an electrostatic clamp. The clamp cycles zones of high voltage across the backside of the wafer to keep it in place, a phenomenon similar to sticking a balloon to a wall using static electricity. To reach nanometer-level accuracy, the plate is independently moved using smaller motors, which is called the short stroke stage. By combining the long stroke and short stroke stages along with measurement encoders, the machine can quickly move the wafer as it's being patterned and maintain an accuracy of less than 1 nanometer, or approximately 4 silicon atoms. Once all the microchip patterns are copied to the wafer, the stage moves back towards the robotic arms where the wafer is unloaded and placed into one of the vacuum load locks, pumped back to atmosphere, and then a separate robotic arm brings the wafer back to the track tool where the patterned and modified resist is washed away using a developing liquid. Finally, the wafer is heated again to further harden the remaining resist. The patterned wafer is then loaded back into the FOUP, which is picked up and brought to a different tool to undergo processing in other ways. Let's close this tool. And that's it for our journey into photolithography. If you have any questions, feel free to ask them in the comments below. We're thankful to all our Patreon and YouTube membership sponsors for supporting our videos. If you want to financially support our work, you can find the links in the description below. This is Branch Education, and we create 3D animations that dive deeply into the technology that drives our modern world. Watch another Branch video by clicking one of these cards or click here to subscribe. Thanks for watching to the end.